Okay, can you see my presentation?
Yes, we do.
Okay, so today I will tell you about a work by Rosay and Rudin. It's a rather old work, I think from 80s, I don't remember the precise year. And it is a work about holomorphic endomorphisms of an affine complex space with of dimension more than one, and it considers the action of these holomorphic endomorphisms and automorphisms on countable subsets. So as we know, and it is actually it is what we study intensively in the laboratory, that that algebraic automorphisms of affine spaces act infinitely transitively. So any finite number of points can be mapped in any other finite tuple with the same cardinality by some automorphism. And but this is not true for countable subsets, and it turns out that it is even not true for countable subsets and holomorphic automorphisms. But still, something can be shown to be true, and there is an interesting theory that was observed by Rosay and Rudin. So I'm going to tell you about it, and also to tell something about new works which try to generalize all those concepts to more general complex manifolds. So yeah, I will start with the main results of my talk. So what results we consider. So everywhere in the talk, n will be greater than 1, is an integer greater than 1, and we consider the endomorphisms of complex linear space with complex affine space of dimension n. And of course, everything is different in when the dimension is 1, because there are not much endomorphism and automorphism really. So the first result is interesting. So if we have, it says that endomorphisms are in some sense infinite transitive. So they act in some sense infinitely transitively on Cn. Let PG be a discrete sequence and W be an arbitrary sequence. And so for any discrete sequence, there exists a holomorphic map with prescribed values. So with value on PG equals WG. And moreover, this endomorphism can be chosen so its Jacobian is everywhere equals 1. So is 1 everywhere. So it's actually not just an holomorphic function, holomorphic endomorphism, but it is an immersion of complex affine space into itself. And we can always choose some such a function. So, but it even works in the dimension 1 if we drop the assumption on Jacobian. So it is known that in almost the same fashion as we can form a polynomial with finite prescribed values, in the same way we can construct a function which has prescribed values on the infinite discrete set. And it is a classical.
Am I right that this map is surjective?
No, not necessarily. So it is important that there are non-surjective immersions of complex plane into itself. But it is easy to construct just an immersion. It's, for example, it's exponential is not surjective, right? And just but it is still an immersion. Immersion means that it is locally and locally of so it has a Jacobian of full degree, of full rank.
I think it's not only an immersion, but also
immersion and submersion. Yeah, it's local homeomorphism actually. Like
holomorphism.
What?
Holomorphism.
Holomorphic. Yeah, right.
If I'm not mistaken,
no.
In a case of n equal to 1, the image is all C except one value, something like this, no?
Except one point. Maybe maybe, but I don't know for sure.
Yeah, it's called Sochowski theorem, I think.
So the point is that if we consider algebraic homomorphism and immersions of affine space into itself, then there it is always surjective, because there are no invertible elements in the ring of functions. So, yeah, in polynomial rings, there are no invertible elements except constants. But when we consider holomorphic functions, there are a lot of invertible functions. So there may be non-surjective immersions. As Grisha said, it's when I say immersions, I mean here, if the dimension is the same, I mean here a locally biholomorphic map.
So it means you have two copies of Cn, right? On your slide, right? So let us take the first Cn.
Yes, we have here a Cn.
So the statement is that if you take any point in this first Cn, then there is a complex analytic neighborhood of this point, such that now our map phi induce isomorphism on this neighborhood.
Yes,
right?
yes.
Mm-hmm. Yeah.
So the second theorem, the second main result is countable transitivity on dense subsets. So if we have two dense subsets of Cn, then we can move one to another by an automorphism. And this is really interesting because it's maybe it may be counterintuitive, and moreover, it is also, I think, shows us how big the automorphism group is, because we have all countable subsets in the same orbit. So the group of automorphisms is actually very, very big. So this means that it is important that those subsets are not ordered. So we do not know exactly which point maps to which point, but we can map. We can find such an automorphism such that the whole set maps to the whole set X maps to the whole set Y.
I'm sorry for a stupid question. What does it mean, discrete sequence?
Discrete sequence means that this is a sequence, and it has no, as a countable subset, it is discrete. So it has no limit points.
Equivalently, does it mean that any element of this sequence admit a neighborhood such that there are no points of the sequence inside of this neighborhood?
Yeah, it is true. So
Ah, I understand. Thank you very much.
So it is a countable subset, which is discrete and ordered. Yeah, and the third theorem is also interesting, and it can be actually called infinite transitivity, but it says that if we have an arithmetic progression, so here E1 is a basis vector, but we can of course choose any other vector. That if we have an arithmetic progression, and if we for every permutation of this arithmetic progression, for every permutation of this countable set, there is an automorphism which furnishes this permutation. So here is, yeah. So for every permutation, every permutation can be obtained from holomorphic automorphism. And actually not only permutation, but any injective map from N to itself can be obtained from an automorphism. And that is an interesting fact. And actually this fact was used as a definition of so-called tame subsets in later works, which I will also mention. And the last main result is that there exists a countable subset such that if any automorphism maps D to itself, then this automorphism should be just identity. So this means particularly that D, such a subset D, is not conjugate to N. So actually the construction of this subset is quite tricky, and I will not provide it, but I will just provide it as a result that such a set exists. But we will see. We will see that this set should be very, very strange in some sense. So yeah, and I think.
Just a second, and can you go to the first slide?
Mm-hmm. First, yes, this is the first slide.
Earlier.
Earlier is my.
Okay, so there is only your name. Am I right that all these theorems are produced by you?
No.
Then this is a big problem that there are no names.
Yes, sorry. I thought that yeah, you are right. So what I mean here is that I follow the work of Rosay and Rudin, and so that every result is theirs, if not stated otherwise. So I'm sorry, I should have corrected my presentation.
And what is the year of publication of this paper?
The year is 1989, I think.
Mm-hmm. So this is not a recent one. This is quite old paper.
1988. Yeah.
Mm-hmm. Okay, and one more comment concerning the third theorem. In the third theorem, you say for every permutation WG. But WG is not a permutation as far as I understand from your text. This is some sequence.
Yeah, it is a sequence with it is a sequence which is a reordering of N. So it's
so the sequence is obtained from N by some permutation.
Yeah, yeah.
There are two concepts in the first course, permutation and I don't know how in English, podstanovka. and permutation is just a sequence.
You can say there is a bijection between n and the W set of WJs.
Okay, I give up. Okay.
Thank you.
One question I have, maybe it's not the right moment, but this set OT Cn, you mean biholomorphic maps between Cn to Cn?
I mean locally biholomorphic.
Locally biholomorphic. So anything particular about the algebraic automorphisms?
So this is not true for biholomorphic automorphisms. It is not true for algebraic automorphisms.
Okay.
And yeah, it is not true, definitely, because I think it may be not hard to construct such a sequence.
Okay, thank you.
It's the same like the polynomial with the prescribed zero. So it is not possible, not always possible to find a polynomial with a prescribed zeros.
If it is an infinite set, it is
yeah, infinite set it is possible.
For finite points we can do, but for infinite, it is.
Yeah, definitely. Yeah, and so I know that maybe most of the participants are familiar with the notion of the int algebraic structure on the group of algebraic automorphisms, and there is also a nice structure of a topology, nice topology on the set of holomorphic endomorphisms of Cn2. And it will be very helpful for us because almost all automorphisms that we will construct will be limits of algebraic automorphisms in this topology. So the topology is called compact open topology. It is heavily used in general topology and in functional analysis, particularly in the theory of holomorphic mappings. So the compact open topology has the basis, which consists of such open sets V, K, U, where K is compact in Cn, U is an open subset in Cn, and the open set is such Fs which map, here is K big, of course, of such functions, such endomorphisms, which map K to U. And it works actually for any complex manifold or topological space. Also, this topology is usually defined on the space of all continuous functions, not only holomorphic. But when we speak about Cn, there is a nicer description of this topology, and this topology can be defined by the series of norms, because NC is a vector space, so we can define a sequence of norms on this vector space and define the topology as the topology induced by all these norms. So
I'm sorry, maybe I didn't understand from what you said above, but now you formulated on the previous slide 4 theorems, right?
Yeah.
What will happen now? You are going to prove this theorem, to comment, to go to some new result?
So of course, I will not give all the proofs, but I will try to give just ideas of, just sketches of those proofs. And the notion of compact open topology is very important here. So it is crucial for the whole story.
So the only aim of this talk is to discuss these 4 theorems, right?
Mostly these 4 theorems, yeah, and also something above it.
Okay.
Yeah, and so this, and I think that this notion of compact open topology goes beyond this application in this particular theory. So it would be also interesting for those who didn't know it. So the topologies can be given by the series of norms. We say that a sequence converges in this topology when it converges by all these norms. So by all the metrics which are induced by these norms. And the basic fact that endomorphism space is complete in the compact open topology. So if there is a sequence of holomorphic functions which converges as a sequence of continuous functions, that it converges necessarily to a holomorphic function. And we will use it because we will construct a sequence of as I said, algebraic automorphisms, which will converge to a holomorphic automorphism. And the automorphism of Cn is a subgroup in endomorphisms, and it is not closed because GLN is not closed, for example, in all linear endomorphisms. But the sequence of automorphisms converges to an automorphism if and only if the sequence converges and the sequence of inverses converges. And we will also heavily use the notion of shears. So shears may be familiar to listeners of this talk because it is just a nice type of triangular automorphisms, and in particular shears can be also not only holomorphic but algebraic. So shear is shear in the direction of EG is an automorphism which is given by the following formula, where f is a holomorphic function which doesn't depend on the ith coordinate. And so shears are holomorphic automorphisms with Jacobian everywhere, with Jacobian equals to identity.
And can you translate shears in Russian?
Sdvig.
Mm-hmm.
And a basic example of shear is an example where f is an entire function on just C, and lambda is linear functional, and u is some vector from the kernel of the functional. Then in some coordinates, the formula here defines a shear, which we will use in the proofs. So we need a lemma, and this lemma is in some sense a lemma about infinite transitivity, but with topology involved. So it says that we can obtain infinite transitivity by automorphisms which are as close to identity in the compact open topology as we want. So if we have some epsilon, greater than 0 and a compact, and this is the data which defines a compact open topology. Then, and we have some finite tuple of points in K, and we have 2 points in a hyperplane which does not intersect K. So we will actually drop this assumption in a moment. Then we can move a point P to a point Q using a shear. And moreover, we can find such shear that it will move points from K not far from itself as epsilon. And the idea of this proof is the following. We choose a linear functional with which equals P, which has the same value on P and on Q, and the value on P is distinct from values on K. Then we choose a unit vector in kernel such that Q equals P plus some non-zero constant multiplied by U. And then we take such polynomial that, and we can always take such a polynomial with G, with the value of G on lambda P equals C, on every point from A every A equals 0, and that the value of this polynomial is less than epsilon on this compact. So and then the shear is defined as in the previous slide. If you specialize Z for some point, for Q on P, or for some A Y, you can easily see that it has all the desired properties. So actually we constructed this shear to be algebraic, and so it just means that we can move one point to another, fixing prescribed points and not moving points in some compact too far from themselves. And here we talk about hyperplane, but if we have we allow not just a shear but composition of two shears, then it is possible to drop the assumption on the hyperplane, so we can just take 2 points not in K and move 1 point to another. And this lemma actually proves the first main result. The first main result about interpolation. Yeah, so the slide is called Immersion interpolation because actually it's just it. Rosay and Rudin also call it Mittag-Leffler interpolation because Mittag-Leffler interpolation is the same interpolation but in dimension 1. So again, if we have a discrete sequence and an arbitrary sequence, then we can find a locally biholomorphic map mapping 1 point to another. And moreover, it's not only biholomorphic, but it has everywhere. It is locally volume preserving, so it has everywhere a Jacobian of equals 1. So here we may choose such coordinates that the modulus of the points in P are ordered, and P1 is less than P2, and so on. And the sequence is discrete, so this sequence of norms diverges to infinity. And we can also assume that no WG has a first coordinate 0. We can always choose such a coordinate system. Then we take such interesting function. As you can see, it is only holomorphic. So here where the idea about algebraic maps breaks. So we use this function which involves exponentials in it, and this function is cool because it is surjective on the open subset where the first coordinate is non-zero, and it pre-image of any point has points of arbitrary big length. And we will then construct this function as a composition of E, this magic function E, and F, where F is a limit of composition of shears. So we construct a sequence of shears from Lemma on the previous slide, and take a limit of these compositions, and we obtain the theorem. So we construct Fk by induction. By induction, we map first k points to map first k points to the same k points, k minus 1 points actually, and we map the point number k to vk. Here, vk such that vk is wk, and such that it is not in an image of a big enough ball. And then we the third property we use the third property to obtain a convergent sequence of automorphisms, and this sequence converges to some endomorphisms. Endomorphism, as it is a limit of composition of shears, it has Jacobian everywhere 1, and the composition of this function E and F has all the desired properties. So that is an idea of this interpolation. Yeah, and this is an improved variant of the previous lemma, also a lemma, and it is interesting by itself because it can be generalized to not necessarily to more general complex manifolds. So when we suppose that we have 3 subsets of Cn, where E is finite subset, K is a compact, and D is a dense subset. So we will use it to prove the dense transitivity. And if we have some point, not from E, from this subset which we will fix, and some epsilon, then we can find a shear with the following properties. This shear will leave all the p's from E unmoved. It will move A to this dense subset D, and it will be not far from epsilon on K. And not just not far from epsilon, but it will not be far together with its inverse. So it will not move any point far from itself, and the inverse will not move the point far from itself also. And so why do I call it a continuous infinite transitivity? Because it says that we can leave points from a finite set and move points from move a prescribed point to some dense subset without leaving, without going far from identity in the automorphism group. So here the proof is also interesting. I don't think I have time to tell it to stop on it. So the idea is that we we assume that A is 0. Then we take some unit vector such that all the p's are not 0 when evaluated on this unit vector. And then we take sequences of unit vectors from Cn and vectors from D, such that they are pairwise orthogonal, and Wi converges to 0 and Uy converges to U. And then we take just a sequence of such shears with here we have an interpolating polynomial, and here we have a sequence of shears. And it is actually as points from D can be arbitrarily close to A, we can be sure that from some big enough I, the third condition will be satisfied. So, and now dense transitivity. And dense transitivity almost uses this lemma from the previous slide. And I want firstly, I want to discuss how. So I will recall the theorem. So if we have two countable dense subsets, then we can move one to another by a locally volume preserving automorphism. So so yeah, we move X to Y by an automorphism. And the hardest part of this theorem is find such automorphism which will have all of Y in its image. So it is actually easy to deduce from lemma such an automorphism which will map X inside Y. So how? So let me show the lemma again. We can here proceed again by induction, and we can choose E to be some set of points from Y, and this point A to be a point from X, and D to be just Y. And we can map points from X to Y using this lemma by induction on every step, leaving all the points from previous steps in this set E. But actually, if we want this map to be surjective, it is a little bit more tricky, and it can be done by enumerating X and Y, and then mapping of first two G points to first two, and then proceeding by induction, we map some two G points of X. It's not the same. It's not a mistake here. They are different points. P and X and Q and Y are different points, but it is some 2J points of X and some 2J points of Y. And then we assume that we have this by induction, and then we construct an automorphism on the next step of induction. And the idea is that we take some point from X, and not just some point, but the first point, which is not a first point in X with this ordering, which is not in this 2J points. And we, using a lemma, we find some shear which maps this P2J plus 1 to Y. And this shear should be also close enough to identity. Again, we use Lemma here, and it is not interesting actually. And we also find a shear which maps yi, which is the first element of y not in these 2j plus 1 elements, and we map it back again to x, but not actually to x, but the image under fj and sigma. And then we construct fj plus 1 as this interesting composition. So what we do here is by induction, as I said earlier, we have 2j points mapped to 2j points. Then we take first non-mapped point from x and first point from y, and first map a point from x to y, and then back from y to x, and that's how we obtain an equality here. And then we just take a limit in this compact open topology, and this limit should exist by some assumptions in Lemma, so that we on every step we choose small and big enough compacts. So this is a dense transitivity, and actually what I wanted to say also, that this lemma can be generalized to arbitrary complex manifold. It can be observed that if what we need actually is infinite transitivity, and that's it. So, for example, so this dense transitivity is true whenever there is an infinite transitivity. Why? Because when we have an infinite transitivity, and what does it mean? It does mean that we have everything in this lemma without the third assumption. So, what we can do, we can find an automorphism such that P is left unchanged and A is mapped to D, but we don't know exactly if we can choose such an automorphism close enough to identity. But it actually is possible to prove that we can choose it enough, close enough to identity. So, so this theorem can be strengthened to the following: if X and Y are countable dense subsets of some manifold X with a dense infinite transitivity, so for example, all non-degenerate toric varieties, then there is an automorphism mapping X to Y. And that is interesting because it is interesting if we can prove the inverse. So I think that I have proved the inverse, but I'm not sure actually. Okay, and that's it with dense transitivity, and this fact actually was very interesting for me because it is actually not very intuitive. For example, it means that we can map all points with rational coordinates to all points with say coordinates which are algebraic numbers by a holomorphic automorphism. And maybe it is not that that counterintuitive if you think of it a bit more, but still it is not very obvious. So, and now I want to show that also another version of infinite transitivity in case of continuous sequences is that we can obtain every permutation of a arithmetic progression. And we start with a lemma again, but it's actually maybe also called a theorem, but I here follow Rosay and Rudin. So here should be I instead of 1, and here also. So suppose that we have two discrete sequences of complex numbers, just complex numbers, not vectors in Cn. Then we can obtain we can construct three shears and the composition of them such that their composition satisfies the following. So it maps maps alpha I multiplied by E1 to beta I multiplied by U1. So the proof is actually very, very easy, and it is enough to prove for C2. We just leave all the other coordinates unchanged. But of course, this doesn't work for n with one n, because first of all, there are not enough shears. But if we allow automorphisms, that it is well known that all the automorphisms of C are just affine transformations. So of course, there is impossible to find an affine transformation with prescribed discrete sequence of values. So in this theorem, it is also crucial that n is greater than 1. And so how we prove it? We first find two functions, two entire functions with values on f with values on alpha I equals beta I minus alpha I, and g equals minus alpha I on beta I. And so these three shears are the following. So the first shear maps Z to Z plus Z1 E2, the second to F Z to E1, and the third Z1 E2. And the composition is the composition. So it is an just a straightforward. It can be checked straightforward that it maps alpha Y E1 to beta I E1, and actually this lemma is more general than the theorem on the first slide. This theorem is just a corollary of this lemma, that if we have an arithmetic progression, then for every permutation of n, there is an automorphism which maps FGU1 to WG. So, and as I said earlier, we can also take here any just any injective map from n to itself, and still we can find an automorphism which maps n to which is this injection when restricted to n. So, and we are ready for the main definition of this talk. So the main definition is the definition of tame sets. And the definition is the following. So a tame set is just a set which is conjugate to the arithmetic progression by some automorphism. And the set is called very tame if this automorphism can be chosen with constant, with Jacobian constantly equals to 1. And I will not prove it, but these two notions do not coincide. So, so there are some tame sets which are not very tame. But think so. The proof is again too tricky to show something, but we will see something different. So this theorem is the first criterion of this notion of the notion of tameness. So decompose Cn into the sum of two smaller affine subsets. So we take just k plus m with ck plus cm with k plus m equals n, and we consider an infinite subset. Then it is very tame if its projection is discrete and every fiber of P of this projection is finite. So that means that if we take every point in the image of projection, that only finite points map to it. So I will not prove it. I don't think that the proof is interesting here.
But I'm sorry, this should be true in this theorem for some k.
It is true for k from 1 to n minus 1.
But we should fix 1k, or this is should. I don't understand. What is the precise statement of the theorem?
Decompose Cn into sum as ck plus cm, and what I forgot here is that both k and m are non-zero, so they are positive. It is important that they are positive, and then the theorem says that if projection of the set is discrete and the projection has finite fibers on E, then E is very tame.
For some decomposition, for
any decomposition. Yeah, so it
there is a big difference between any decomposition and one decomposition. If I found one decomposition and this condition is true, so I'm happy we already have very tame, or we should choose, or we should check something like this for any decomposition.
No, it's if for some decomposition this holds, then the set is very tame. So of course there are millions of possible decompositions here. So this theorem actually shows how very tame sets should be pathological. So because it seems like it is not, it is almost impossible to find such a subset, such a discrete subset, so that for every projection, such that for every decomposition and for every projection, it is not the image is not discrete, or the image is discrete, but it doesn't have finite fibers. So it shows that the notion of tameness is, so it is hard to construct non-tame sets. Yeah, and corollaries is the following. So if some subset is contained in a hyperplane, then it is very tame, of course, because we can take a decomposition C n minus 1 plus C and take just the projection, which will be an identity on E. This also shows that the union of a finite set and the very tame set is very tame. So why? Because if we should check this only for this projection or progression, yeah, because we can always conjugate a tame set to by an automorphism to an arithmetic progression. And if we attach a finite set to an arithmetic progression and then take a projection to the first coordinate, then then the image will be discrete, and it will necessarily have finite fibers, because the image of n discrete and has finite fibers, and we only attach a finite number of points. And every discrete infinite series is the union of two very tame subsets. So if we have any discrete subset, and it is necessarily a union of two very tame. And why? So the last assertion is not really obvious, but we can take the following. So we consider a decomposition with k equals 1, and we divide E into two subsets with when one projection is greater than another, and vice versa, when other projection is greater than the second projection is greater than the first. And E2 satisfies the assertion of a theorem for the first projection, and the second for the second projection. So that is also interesting, how every subset can be decomposed into two very tame subsets. This is also a good characterization, that suppose that we have so we have a subset E, it is infinite discrete, and we have chosen a coordinate system in Cn such that for every element of E, and every coordinate of this element is greater than 1 by absolute value, then E is very tame. So this means that if the set is not very tame, that for some coordinate system it has some elements with arbitrary small coordinates, because actually we can because we have an automorphism which just a multiplication automorphism, actually we can replace here 1 by any complex number, any positive real number. So the proof is the following. Consider the multiplication of all the coordinates, and if the assumption holds, then this function is this multiplication, the values of this function is always greater than 1, and moreover the image of E under it is discrete, and the fibers of it is finite, because it is easy to show that levels of these functions are compact. So we cannot have an infinite discrete subset in a compact set. So we have the image of E discrete in C, and each fiber, each element of E which has a value of lambda t is finite. Then we choose a holomorphic function such that on lambda t it has t. So again we use an interpolation here. As you may have observed, we use the holomorphicity assumption very strongly throughout the talk. So then we define the function as following. So we only change the first two coordinates, and one can check that this image of E satisfies the hypothesis of the projection theorem on the first coordinate. So we again decompose as C plus C n minus 1, and this satisfies it. So so that's it. That's the proof. I do not expect that you have fully understood it, but that's the idea. And here we use the assumption. That is, if we use the assumption here, so if and actually we could also assume that it's just not one, but any non-zero constant. The important part is that the image of P is discrete and fibers are finite. So yeah, so yeah, this is one more characterization, and it again shows awareness and of non-tame sets. It shows that those sets are pathological. Then interesting fact which Rosay and Rudin consider is avoidable and an unavoidable subset. So what does it mean? And the proposition, so it means the following. So the following is the proposition. If we have a tame subset, just tame, not necessarily very tame, then there is a biholomorphic map, so that the image of this map does not intersect E. So this is this is a biholomorphic, so it is injective, and it is a local homeomorphism. Yeah. So, and if E is very tame, then we can choose this biholomorphic map to be also a locally volume preserving map. That is interesting because it is contrary to what happens in the algebraic world. In the algebraic world, we do not have any injection, any how to say, yeah, any injective map from Cn to itself, but in holomorphic world it happens, and actually for tame sets we can always choose a map such that it avoids it. So this means that tame sets are avoidable by holomorphic maps. So and the basic fact here is just the following fact, that there exists a biholomorphic map with the image not equals the whole Cn. So and this is like a basic fact that such a map exists, and so we have an image. We have an image being homeomorphic to Cn, and this means particularly that the complement of the image is unbounded, because if it was bounded, that for example we could say that it has a non-trivial it would have a non-trivial homotopic group, one of homotopic group, for example. But I think it can be proved in many ways. But we need that the complement of the image is unbounded, and so we can find a very tame subset. So why we can find it? Again, by projection theorem. And if we can find some very tame, then we can take a conjugation by an automorphism. And so we have proved this theorem for any tame set. And yeah, here we find a very tame, and if it is tame, then we should drop the assumption of this unity assumption. And the theorem proved by Rosay and Rudin that there exists a discrete set which is unavoidable by non-degenerate holomorphic maps from Cn into Cn. So there is such a discrete set which is necessarily non-tame. So that this is how they prove that not every countable discrete subset is conjugate to each other because it has an unavoidable subset. But the construction is too complicated, so I decided not to include anything here because I just didn't even manage to extract like a sketch from it. Yeah, and something I have about 10 minutes, so I will yeah, and what I also haven't mentioned. I have mentioned it, but only in the beginning. So now we can return to the beginning, and it was the fourth theorem. So that there also exists a countable subset such that if any automorphism maps D to itself, then D is necessarily an identity. As Rosay and Rudin constructed, it is not the same D as the previous theorem, but this is also an example of non-tame subset and also a counterexample to a possible conjecture about generalization of the previous theorem about permutations. So there exists such strange subsets which are called rigid as opposed to tame. So this is a class of subsets which Rosay and Rudin called rigid. But again, the construction is tricky and rather technical, so it is wouldn't be not a great idea to include it here. They decided also to include some new results, which is a work which is a recent work. It's of 2017, and the work also by and this work by Winkelmann and the work by Andres and Ugolini from 2018. So they, I think they were independent, but they have cited one another after the publication. So if X is a complex manifold, and then an infinite discrete subset is called by Winkelmann weakly tame if blah blah blah, actually, because it is not easy to understand fast. So if we have some exhaustion function, which means that it is that it exhausts actually X, so it is I actually can't say the precise meaning of exhaustion here. I think that the value sets of this function should be compact, and every map. Yeah, this function is also not necessarily continuous, and every map from D to R plus, so there exists an automorphism such that the value of rho on automorphism is greater than this value. So for all X in there. So this is rather strange definition. But
the exhaustion function. Suppose that this function takes values that are not greater than 1, say. And this another map, it maps elements of our set to some bigger real numbers. Then we have no chance to have such an equality. So something is not clear.
Yeah. So as I said, I think that it means that that level sets of these functions are bounded, and so they should be compact. I think that's enough to assume. Yeah. So I think that's that's what they mean. Or not, yeah, maybe not compact, but bounded. They may be not closed. And the next definition is easier to understand, and it is more reasonable, actually. But it's not equivalent to the first one, so it's called strongly tame if every injective map can be obtained from an endomorphism. Yeah, and so we easily see that this is the definition of Rosay and Rudin, that was one of our theorems, that the definition of Rosay and Rudin implies the definition of Andreessen and Ugolini. But they actually prove that for Cn, all these three definitions are equivalent. That was what I think Andreessen and Ugolini proves. And also they say that these two notions coincide for SLN. And they also, I think, give an example where these two notions do not coincide. I don't remember exactly where. But for Cn, it's these two definitions are equivalent, and they are the same by Rosay and Rudin. And I will just briefly state the results by Winkelmann. So here are results by Winkelmann, and they are generalization of results by Rosay and Rudin. So the first is that any two-tame discrete subsets in SLN are equivalent. And this is actually what is a definition by Rosay and Rudin. They define a tame subset as equivalent means conjugate by an automorphism. And this means that yeah, this is the same as Rosay. By definition of Rosay and Rudin, we have this automatically. Yeah. Here identifies certain discrete subgroups as tame discrete subsets. So particularly SL2 Z of Gauss numbers is a tame discrete subset. And as it also happens in case of a affine space, if we have a one-dimensional Lie subgroup, then every discrete subgroup of a maximum here again. What should be here is that any discrete subgroup of a one-dimensional subgroup is tame. So what we have in case of Cn, that we have, if we have a discrete subset of hyperplane, then it is necessarily tame. So that's what analog of the second. Then every discrete subset of SLN is the union of n tame discrete subsets. It is interesting, as we have seen, that in case of Cn, it is union of exactly two subsets. It is also interesting that every simple complex Lie group admits a non-tame discrete subset. So this notion is not unique for Cn. Every injective self-map, again, of a tame discrete subset of SLN extends to a holomorphic self-map of SLN. And this is actually an equivalence between these two definitions. And there exists some threshold function sequence which also exists for Cn, and it is also in work of Rosay and Rudin, but I haven't mentioned it because it is rather not so interesting and rather complicated. So there is some sequence which can assure us that some some subset is tame if values of this of the exhaustion function of this sequence is greater than this threshold sequence. And the next slide about counter examples by Winkelmann. So the first counter example is that on Cn without an origin, there exists a discrete subset. There exist discrete subsets which are not the union of tame discrete subsets, which is not a finite union. On the product of disk and C, there are tame discrete sets which are not strongly tame. Yes, so these notions are not equivalent for this manifold. And there are permutations of tame sets which do not extend to be holomorphic self-maps. So it's these two sentences means the same actually. There exists inequivalent tame discrete subsets, also interesting. So we see here, this is example of this manifold. And the reason is that there are too few automorphisms because this set is not, I think it is called a hyperbolic. This manifold is not hyperbolic, so it is small in some sense. The disk is, as you know, probably the disk is not biholomorphic to the whole complex plane, and there are very few automorphisms of a disk, so there are very few automorphisms of this product. And there is not such threshold sequence on Cn without an origin. So that's it. Yeah. Are there any questions?
Isn't it better for the automorphism of algebraic automorphism of Cn into endomorphisms continues?
I can hear you because it's some noise in the background.
Okay, well, maybe I will ask you later.
You can ask in chat probably. While Grisha is probably typing, maybe more questions.
Maybe I can do a short comment, because what was the idea of this talk? Some of us study infinite transitivity, and by infinite transitivity, we means transitivity on m tuple of points for any positive integer m. And we study this in algebraic setup. And it's quite interesting to ask the same question for not just finite of arbitrary order, but infinite sequences, say for countable discrete sets. And it turns out that such a problem was studied in complex analytic settings where it's much more natural to study it, not in algebraic settings. And it was done chronologically before algebraic case. So this is a paper by, how to pronounce correctly, Rosay and Rudin.
Mm-hmm.
And the aim of Boris' talk was to present these results. And now we have some continuation in a paper of Jörg Winkelmann and other colleagues which were mentioned in this talk. I don't know whether now we have a good impression about this result on transitivity on countable sets, but at least it was an attempt to overview such results. Okay, now my musical pause is finished, and we have a question from Grigory.
Mm. Yeah, also these results show how actually it should be hard to study holomorphic automorphisms and endomorphisms of Cn. So it is there are books wrote about this subject, and still there are not many particular results. And so to the questions of Grisha, So is the embedding of algebraic automorphism as endomorphisms or automorphism group of Cn is continuous as in the topology, as int topology? And here I assume that yes, that it is continuous because the int structure is constructed from polynomials of degree not greater than some n, and in the compact open topology, these finite subsets are closed, and so the inclusion should be continuous. And then when we proceed to the limit, I think from categorical arguments, this should be continuous. And for the second question, is endomorphisms group closed in holomorphic endomorphisms? It is not true, because also here in this talk we constructed a sequence of algebraic shears which converge to a holomorphic shear. So it is not true that that endomorphism is close, and it is actually just for endomorphisms. It is very easy to see. Just consider the exponential function as a limit of polynomials. So it is obviously is a limit of algebraic functions which converge to exponential. And the closure of endomorphism is, if we talk about endomorphisms, yeah, the polynomials. So endomorphism is just polynomial functions from Cn to Cn, and it is known that the closure in the compact open topology is the whole set of holomorphic endomorphisms. So every holomorphic endomorphism can be approximated by an algebraic endomorphism. It is and for automorphisms, I'm not sure. Probably it is also true. Actually, this is also studied by such authors as Forstenstrik and Kuchenbach. So yeah, it is studied. I've seen it somewhere, but I don't know have a precise statement. I think for automorphism it is also true, and every holomorphic automorphism can be also approximated by algebraic automorphisms.
Okay. So are there any more questions, comments, propositions, suggestions?
About orbits of holomorphic closure of a group. Oh, that's hard. I don't know actually. I have no idea about orbits. It's it should be. I think maybe not. If but for C. I think if the orbit itself is not closed, maybe it can have a limit. I don't have any idea here.
Okay, so let us thank to Boris